The recent California atmospheric rivers were not just storms, they were a display of a new scale of destruction, turning vast farmland into standing lakes. These events indicate that the physical properties of our atmosphere are behaving differently than they did for the last century, holding and releasing water with a force that defies traditional weather patterns. The math behind this shift is nearly 200 years old. In the mid-19th century, physicists like Rudolf Clausius mapped out the exact relationship between heat and the pressure of water vapor. This established thermodynamics proves that the flooding we see today is a predictable physical consequence of a warming climate. This chart shows the Clausius-Clapeyron equation's baseline math. For every degree of global warming, the atmosphere's water vapor capacity increases 7%. But convective storms break that baseline. They act like a vacuum, pulling in and concentrating extra vapor over a localized spot. This process is fueled by rising ocean temperatures. They feed extra latent heat into these storms, which acts like an engine, spinning the systems faster and drawing in even more moisture. These extreme storms are known as Super-Clausius-Clapeyron events. During Hurricane Florence, the volume of rain dropped on these neighborhoods far exceeded the 7% baseline, creating the catastrophic damage seen here. The warming atmosphere has become a highly efficient storage system, designed to gather and then violently dump enormous volumes of water. As the sky is becoming geared to release record-breaking moisture, we have engineered the ground below to be incapable of absorbing it. When heat waves occur just before heavy rain, they bake the topsoil dry. This changes the soil's composition, causing it to physically repel water rather than soaking it up. Modern agricultural practices exacerbate this. Tilled fields with low residue crop cover lack the vegetation required to slow down the movement of water across the land. The result is the formation of ephemeral gullies, temporary, high-energy rivers that carve through bare fields, devastating water quality and tearing away tons of topsoil in a single storm. We have effectively terraformed our rural landscapes into slick, high-speed runways for incoming floodwaters. In urban environments, the collision is more severe. Sprawling layers of impermeable concrete and asphalt trap water on the surface, leaving it nowhere to go. Our legacy stormwater systems and culverts were designed using 20th century models. They are now mathematically too small to handle modern supercharged deluges. This creates what the IPCC calls hard limits to adaptation. For many low-lying communities, the mismatch between old infrastructure and new physics is leading to mathematically unavoidable damage. We are facing a physical crisis, where a sky designed to flood meets a ground designed to repel. Reversing this trend requires two simultaneous actions. We must reduce the sky's capacity to hold water, while redesigning the ground's ability to absorb it. This chart shows the necessary path for the atmosphere. To prevent the sky from holding even more vapor, global emissions must peak before 2025 to stay within the 1.5-degree warming limit. Staying on this path requires an immediate phase-out of fossil fuels and the rapid scaling of carbon removal technologies to reach net zero by 2050. To handle the flooding that is already inevitable, we must also systematically unpave our urban environments. We can replace asphalt with permeable pavements, install bioretention rain gardens, and deploy underground storage trenches to catch runoff before it becomes a flood. Restoring natural wetlands and floodplains allow them to act as massive natural sponges, absorbing the overflow when rivers exceed their banks. The floods of the 2020s are the direct result of heat meeting an impermeable landscape. By rapidly decarbonizing the atmosphere and redesigning our terrain to work hand in hand with nature, we can secure a livable future.